Okay, everybody, we're about to get started. This is the Network Management Working Group. I'm Niall Buchanan. We're here to hear from Nalini Elkins on migration to post-quantum cryptographic suites, how and why. You will be remaining muted for the entire session. For the Q&A at the end, I will unmute the lines. Nalini?
Okay, thanks so much. Can you hear me okay?
Yep, we can hear you.
Okay, perfect. So let's go ahead and get started. So what's the problem? Well, the problem really is that within the next 5 to 10 years, there will be a quantum computer which is sufficiently powerful to break our current encryption suites. People are working on this today, and this includes many people, not just in the US, but all over the world. The IETF, NIST, and many other standards groups are working on ciphers, which will be difficult, if not impossible, to break. But how to migrate to these suites, that is the problem. So sorry, this thing is getting away from me. So what is exactly the threat? So what people are doing now is they are storing your network traffic today. The network traffic today is probably encrypted. Certainly, I hope so. They cannot break it today, but what they're thinking is that in the next 10 years, they will be able to break it. And that means they can read your data. And in particular, think to yourself, if you're the Department of Defense, or actually many other people, do you really want all that historical data being broken and people being able to read it? I assume the answer is no. So what's going on? So the NIST, the National Institute of Standards and Technology for the United States, has just approved some post-quantum crypto algorithms, and I will share those with you at the end. And this is what they say is the threat, and I will go through so that you understand what it is that they're saying. And they're talking about certain things, certain cryptographic algorithms, such as AES, or writ large, the symmetric key type of algorithm, and then certain types of public key and signature algorithms. As I say, I will go through a number of these so that you understand what is the risk. So let's talk first about symmetric key algorithms and what they say. Symmetric algorithms are really less at risk. So really all you need to do is make the key bigger. So what are symmetric key algorithms? So symmetric algorithms use the same key for encryption and decryption. That's relatively easy to understand. You use 1, 2, 3, 4, or as in this picture, you use the encryption key Tiger. And to decrypt, you also need that encryption key, the same encryption key. The problem with symmetric key algorithms is, however, both the sender and the receiver need to have that same key. And in fact, that is why asymmetric or public key algorithms came about. Before these algorithms, banks used to actually send human beings, couriers, with keys to give the keys to each user. Clearly, that is not a scalable or sustainable solution. So let us think about why NIST is saying that larger keys are important to break symmetry, for this. And so for symmetric key ciphers, actually any cipher, the most basic method of attacking it is brute force. That means you try every single key that might work. Say, let's say you know that it's a 5-character key, something like that. So you can start with A, and then go on and see how many, see which one works. Clearly, if you're going to do that, then the bigger the key, the harder it is to break. Because even if it takes you 1 nanosecond to check each key, if you have a very large number of keys, well, that adds up. And so that makes brute force attacks much harder to do. And hence, AES is saying that really what you should do is use a larger key size. Let us now talk about RSA. RSA is the public key algorithm, which is most often used in today's public key cryptography. That is changing, but as of today, I would say in large enterprises, which means like large private enterprises, banks, government agencies, and so on, the kind of people who would have IBM mainframes, quite often you are using RSA key exchange for public key algorithms. So how do asymmetric algorithms work? So asymmetric algorithms have a different key. So symmetric algorithms have one key. You encrypt with Tiger, and when you decrypt, you use the same key. Now that's easy to understand, but what about asymmetric key? How in the world is this going to work? You use Flower to encrypt and you use Tigers to decrypt. I tell you, when I first found out about this, I could not get this through my brain. I'm like, what in the heck is going on? And clearly, there has to be a mathematical relationship between those two keys. Otherwise, it would not work. But what exactly is that mathematical relationship? And I'll get into that for a bit. So asymmetric algorithms are used in what's called PKI and digital signatures. What a protocol like TLS will do, they will use asymmetric or public key algorithms to transfer over the symmetric key. This makes it so that you don't need an actual human being to go back and forth with the keys. So you can see it is very, very important to have the public key encryption. And so what we have is called the private key and the public key. The private key is known only to its owner and it should not be divulged to anyone. And the public key is known to anyone. So there's another challenge here. How can you create an algorithm whereby you make one key known to everyone, but you can't figure out what the other key is? These are very, very interesting challenges, and I'll tell you the history of how they were solved. Because then once you understand the concepts, then you will be in a much better shape to cope with this new world that we're coming into. So in public key systems, what you need, it needs to be quite simple to generate the public key from the private key. You need to be able to do that very rapidly, but to go the other way, to go from the private key or go from the public key to get the private key, that has to be very, very hard, because remember, you're making the public key open to everyone. Everyone knows that public key. And in the past, it was thought that you would need years to break some of these algorithms. The RSA algorithm that we're talking about was invented quite a long time ago by Ron Rivest, Adi Shamir, and Leonard Adelman. And this is hence the RSA. And it was interesting. I had the pleasure of meeting Ron at a conference the other day. He is of course one of the heroes of our world. And these algorithms rely on what is called the hard to invert function of factoring prime numbers. Now, you know, one of the things, whenever I have seen things like that, you know, what happens is that people start falling asleep right after the rely on. It's like, what are you even talking about? It's actually not that complicated. So let me explain. And the reason I'm explaining this too is because the whole things you'll see on quantum computing will talk about this thing of what can they factor. And so if you understand it, then you will understand what the whole story is. So let's talk about what does it mean to have a hard to invert function. What you want is something which is hard to undo. Let's take one example. Function 1. You give me the number 2, I give you the number 4. You don't know what the algorithm is. Somehow I'm just giving it to you. You give me 5, I give you 10. I think I'm seeing a pattern. You give me 9, I give you 18. So now you go, okay, what you are doing is doubling. So if I go backwards, I say, if I give you 22, what is the number you gave me? Well, it was 11, right? Because I'm using doubling. That is called an easy to invert function. That is where the algorithm is very easy to deduce if you have the two parties. So if you want a hard to invert function, then let's look at this. So let's say you give me the number 2, I give you 1. So I'm thinking, okay, maybe you're thinking, okay, so maybe I'm having, okay, fine. That's my working hypothesis. You give me 5, I give you 2. You're like, okay, well, maybe having, but then, I'm leaving off the odd portion, all right? But then how about this? You give me 56 and I give you 35. And you're like, okay, all bets are off. I don't know what it is. So if I give you 3, it's so you don't know what the original number was. It's not so easy to see what the pattern is. So what the answer is that I'm using the modulus or remainder function. The modulus turns out to be one of those things that can be used for hard to invert function. And really the other thing I did is I used an initial number. I used a seed. So I say, so I start with the number 707, I divide it by the number you gave me, and I give you back the remainder. And so then if you have that, it becomes very difficult to know what the original number was. This is the kind of thing that people are working on and have been working on for years, is more and more and more complex, hard to invert functions. In fact, the function that is used in RSA is the function which is the hard to invert function of factoring prime numbers. So let us think about what does that even mean? All right, so let's start with what is a prime number. So the prime number has exactly 2 distinct divisors, one and itself. For example, the number 7 cannot reduce down to anything else. It can only divide into 1 and itself. And these are the smallest 25 prime numbers, the ones under 100. And you can see there's quite a list here. So, and of course, they can get bigger and bigger and bigger. And when you do prime number factorization, this is a list of all the prime number factors of a given number. For example, if I want the prime number factors of the number 15, it is 3 and 5. Those are the 2 prime numbers which will create 15. Clearly, not every number has distinct prime number factors. You have to have two prime numbers, two or more prime numbers, which are multiplied together to get the number that you want. And so prime number, when you do prime number factorization, you don't include one, but you use every other prime factor. For example, if you want to factor 8 into its prime number factors, you have 2 times 2 times 2. So those are the 3 prime number factors of the number 8. So why is this so hard to invert? So before the whole idea of quantum computing and all of that came along, it was thought that prime number factorization can only be done via brute force. That is, there is no algorithm which will allow you to do prime number factorization easily. So this is, sorry, I don't know why this thing is coming up. And so this is, I'm not going to go through this, but this is a sample of the RSA algorithm. And you can see some of the things we've been talking about: prime numbers, modulus. It turns out that exponentiation is also hard to invert. You can see all these things in the RSA algorithm. And in 1977, the Scientific American invited readers to factor this large prime number into its 2 prime number factors. And it clearly, you win, you know, the prize was for the glory of having done that, not for the $100. And it was solved 17 years later using a grid type effort with many people working on it. And today the numbers used for C, which is the seed for RSA, if you will, the numbers are much larger. So it was thought for a very long time that RSA was not crackable in a reasonable time frame. And this is why RSA is used in much of cryptography all over the world, in the financial, government, everywhere, in many sectors for cryptography. So a couple of things now. When you go to TLS 1.3, TLS removed RSA. Why? Because, as we said, RSA depends on prime number factorization, which before people thought it could be only broken with brute force and other attacks. But now we have other things. And I will talk more about this whole area in the TLS 1.3 and going dark presentations. Let us now think about quantum computing. Quantum computing works very differently. They are better than traditional computers when it comes to factoring. You notice why we are talking about factoring. This is why I spent time talking about prime number factorization. This is one of the big things, that big ways of measuring quantum computers, is what can it factor. And, you know, again, quantum computing is very difficult to understand, frankly. And most people will say, you know, we don't know why it works, we just know it does work. Essentially, quantum computing has 3 states. They have a bit, which is called a qubit. It can be 1 or 0 or something in between. And again, I have to say, when I first heard this, you know, we all laughed. We're like, really, you have 3 different possibilities? Well, they laughed last. So what happened is 1994, Peter Shor, who was at MIT, he came up with an algorithm to factor large numbers, which were which were prime number, they were the product of two prime numbers. So prime number factorization. He said, if I had a quantum computer, this is what I could do. Yeah, but he didn't have a quantum computer. So along comes someone else, Isaac Chang, and he managed to use this algorithm with a quantum computer to factor the number 15, but not much more. Now, of course, that's laughable, right? Because, you can get a high school student to say, what are the prime number factors of 15, right? In 5 seconds, it's like, okay, 3 and 5. Clearly, we don't need to spend 20 million on that. But now things are going larger and larger. This is the initial progress. And you can see what they're talking about. They're saying 15 has 2 factors. How many qubits do you need? And which algorithm? You can see other algorithms have come up. So Shor, these are the initial ones that Shor did. Then there's the minimization algorithm, but now we're getting to some more interesting numbers. So we have the number 291,000 something, and you need 6 qubits for that. And let's keep going. Now we're starting to see something. Okay, this is from IBM's roadmap of quantum computing. Again, you can see what they're talking about. They measure it by the number of qubits that you have. Here we are. This is 2019 with 27 qubits. 2022, we're at 433. Wow, but now we're getting up to 1021. We're moving along quite rapidly. And you have to think to yourself, well, my goodness, if IBM is doing it, clearly others are also. Well, indeed, they are. Google, of course, not to be left behind, is building quantum computers and spending billions of dollars to do this. And it's all well and good for Google and IBM to do it, but what you really don't want is people that you might consider to be in a potentially adversarial position having these things. That becomes a slightly different problem. So let's keep going. Let's talk about some other algorithms, and then we'll talk about some potential solutions too. So we've seen how RSA is no longer secure. You might have heard about elliptical curve cryptography. That is also considered not secure. That's very interesting. Elliptical curve cryptography it was seen as one of the big factors which led to smaller key sizes that were equally secure. And again, elliptical curve cryptography is used everywhere, and in particular in smaller or IoT devices. I just got an email just this morning where NIST has approved something else for lightweight cryptography that is post-quantum crypto proof. They call it lightweight cryptography for these sensor and IoT type devices. But let us talk about ECC. So what ECC starts with, we need 2 things. We need, what is an integer? Well, integer is a whole number. It can be positive or negative. What is an ellipse? An ellipse is an oval-shaped curve. It is not a circle. It is oval. So why do we know about these things anyway? Well, Johannes Kepler said that he figured out that planets move in an elliptic orbit. So for many, many years, we have had the science of ellipses and where points are on ellipses. In this case, the points that we are considering are planets. So this is the basic elliptical curve equation. I won't go into it terribly, but it is a relatively simple equation. where you get this, you have A, B, and C are integers, and you get a particular curve. Let me show you some. For example, this curve, if we say let A equal to -1, B 0, and C 0, this is the kind of curve that you get. And so if you give another set of numbers, if you have A equals 1, you get a different curve. Here's some more curves. My goodness, those are very, very interesting curves. And so the main operation is called point multiplication. This is thought to be hard to invert. And I tell you, I have to say those curves make my head hurt. And so you can see why elliptical curve cryptography and point multiplication would be hard to invert. And you will see today, if you start looking into delving into the TLS packet, you can see the ECC, and you can see that, they say we're using curve 2559 or some such thing. And you'll see that all over. This is what they are talking about. So what's the good news? Where are we at now? For general encryption, what NIST has said is when we're going to use secure website, this is what we want to do. We want to use the Crystal's Kyber algorithm. It has relatively small encryption keys. If we want to do digital signatures, then we have these three: Crystal's dilithium, Falcon, and Sphinx Plus. And you can see these are the first 4 quantum resistant algorithms. And I will say that this was news that was widely anticipated and looked at. People were checking which ones would be announced for quite a while, as I recall. But now what? How do you actually use these cipher suites? You yourself are not just allocating them. They have to be embedded in a particular protocol. For example, here is a TLS 1.3 hello packet, and it's telling you what starts, or TLS 1.2 packet, sorry about that. Yeah, and you can see what it is using, and you can see it's using a lot of these suites: ECDHE, RSA, AES. And so you can see there's a whole science of decrypting what these suites are saying, what the cipher suites are. But basically it's telling you which hash algorithm and which cipher suite, which key exchange you will be using. So the point being that you have to have a protocol which uses this. Well, again, all well and good, but how do you migrate? This is the story of TLS. TLS was defined at the IETF, at the release date. I'm talking about the release date at the IETF, when it became an RFC. You can see 1.0 was January of 1999, took quite a bit for 1.1. And then you can see the end of life, June 2018, deprecated these suites. And then 2008, TLS 1.2 came about. TLS 1.2 does not have an end of life. And then TLS 1.3 came along 10 years later. Each time has been a long, painful, and costly migration. I will tell you, I talked to somebody who works for the credit card industry. They're part of the infrastructure of the credit card companies. And even though they were going to get fined for still being on TLS 1.0 or 1.1, they said, we just don't even know where all our endpoints are. They may be at gas stations in outer Mongolia. And how the heck are we going to get these people to convert when we don't even know who they are? And this particular gentleman said, I have 2 guys assigned full time to keep people converting. And even then, I don't know if I'm going to be able to do it. So it is a long process. And the thing that people are very, very eagerly not anticipating is when or if TLS 1.2 is deprecated. That will be a very, very painful news indeed. So one of the things people are working on at the IETF is hybrid key exchange. And they're putting this stuff in TLS 1.3, not in TLS 1.2. And again, it's motivated by the transition to post-quantum crypto. And basically what they're saying is that you'll be able to use more than one key exchange algorithm. You may, if you have one of the old ones, you can get one of the new resistant ones, which will ease your migration. But then you have to start moving to TLS 1.3 also, which has its own issues, as I will talk about in another presentation. So what are some of the problems here? Well, the protocol versions have to match on both sides. You can't have TLS 1.2 and even a particular cipher suite. You have to, both parties have to agree on not just the protocol version, but the cipher suites that you're using. The problem becomes not on the server side, but on the client side. So what exactly is a client? Well, on it sometimes, well, sure, it's a computer or a cell phone, but I was talking to some folks who are with Department of Defense the other day, and they have some kind of thing, it's like a contact lens that you put in, which is shaped to your iris, and that is your single sign-on. That is what allows you through the whole building and has your access. So it's kind of funny. They consider the human being as the client, a different way of looking at it. And here's some more on what people are working on. People are working on implanting chips in your brain. And this one is quite interesting. And it is actually quite useful. There's a startup called kernel.co, and they're working on a chip that will be implanted into the part of the brain that stores your memories. So if you have Alzheimer's, then you might be able to access that. So a very useful product, but imagine where these memories might be stored. Well, you know, they're thinking we'll store it in the cloud. Oh, interesting. What if I can hack into that? What if I can hack into your brain? My goodness, the possibilities are endless. So if you are in a regulated industry, you have other challenges. Here's a bulletin which talks about migrating away from the old TLS 1.0 to 1.1 versions. And so this is something you always have to be aware of, is that if you're subject to regulation, whether it's by the government or in financial organizations or whatever, or HIPAA, there may be more reasons or more impetus to migrate. And I will say that I do hear a great deal of conversation in the industry, in the federal government, US federal government, about migration. The question, of course, is how to do it. It's easy to say you need to migrate, but how the heck are we actually going to do it? So yeah, so there we are. Any questions from anyone?
If anybody's any questions, they can unmute themselves. I've got no questions in the chat, Nalini.
Okay, okay, great. Well, please, you have my email. Please feel free to email me with any questions. And thank you so much for the opportunity to speak.
Thank you very much, Nalini. We've got no questions.
It's either I've totally confused everyone or I was clear. Yeah.
Okay. Okay, I think we'll close it off now.
Okay, thank you so much.
Thank you very much, Nalini. See you again soon.
Bye.
Bye.
Bye.